Hello again. Here we are doing part 2 of our quick review and overview of building structures. So today I want to take a look at structural systems. Last part 1 we looked at elements and sections and loads and stresses and forces. Now I want to take a bigger picture view of buildings as a whole. Now, one of the approaches we take is much like when we do XY plots on graph paper, is to use a Cartesian approach. So that means that loads, structural loads, kind of resolve themselves quite naturally into two broad categories. Vertical loads, one could call that the z-axis, and then we have the lateral loads, which are in any random distribution along the xy plane in line, parallel to the ground. So the vertical loads, of course, dominated by gravity loads, although we also have to think a little bit about wind loads that can add suction upwards or downwards. And then the lateral loads, which are normally approaching zero, but can be quite significant side to side from a seismic point of view or from a wind load point of view. So when we approach the design of a building structure, superstructure system, we almost always want to resolve the loads into those gravity vertical components and lateral components. It just so happens our buildings are also naturally resolved into vertical and horizontal axes because, well, humans like relatively flat surfaces to walk on and to produce factory components on and to worship on and to go to school on. Whereas the vertical components, well, we like our components to be vertical because we ourselves tend to spend a lot of time vertically. And so this actually kind of lines up quite well. When you move into structural systems where we violate these rules of horizontality and verticality, such as a Frank Gehry type building or Daniel Libeskind, it actually causes a fair amount of challenge. Not that we don't know how to do it, it's just it costs a lot of money, takes a lot of extra work, is much more difficult to build, often doesn't work as well, and there's reasons for that. There are a lot of good reasons for this vertical horizontal resolution of loads. So we're going to look into lateral loads in this part and consider things like the structural system that deals with them. So again, wind loads, seismic loads are those lateral loads we're going to focus on. I'm not going to ignore gravity and dead loads here, but I'm going to focus on the lateral loads first as something that you probably haven't spent a lot of time on in your current studies to date. So to start, let's look down on a floor plan, resolve into the XY plane, and we're looking at lateral loads that may be coming from any direction. With an earthquake or the wind, you can't be sure whether it's going to come from the north, the south, the east, the west, or any point in between. And so we are generally designing for the worst case direction or worst case load in any direction. And to do that, we have to have some load capacity that can act or be resolved into the X or the Y direction. So obviously one way to do that is to have a lateral load resisting element shown here in bright red that is 90 degrees to another one. So you have two orthogonal axes and two lateral resisting systems. Now to take the loads from, say, the walls and the floors, the walls are what are collecting a lot of the wind loads. The floors actually impose a lot of the seismic load because that's where a lot of the mass is. But of course the walls also produce seismic loads. That load needs to be transferred over to the lateral load resisting system. And that means that we need to have some stiffness in the floor system to take the loads that are lateral and transmit them to those lateral resisting systems shown in red. And so the structural diaphragm is the label given to that function. It almost always is a roof or a floor system But if we don't have a roof or a floor, we have to replace that with some other way of transferring these lateral loads from the perimeter to the lateral resisting system. For that reason, it's a challenge if you have a large hole in your floor caused by an atrium or a skylight in a roof. If the hole gets too large, that horizontal diaphragm gets either too weak or too flexible. And so that's always something that needs to be managed when we are designing a structural system for a building. Complex building shapes can easily be managed, and you don't need to have just two orthogonal load-resisting systems. It's just that we will resolve, using vectors, of course, and trigonometry, we will resolve the x and y resistances to match the x and y imposed loads. And this allows us to have odd-shaped in-plan buildings. And the one that's shown here, that particular shape, you can see how you wouldn't want to ignore, just put all of the resisting in the bottom left, because now the diaphragm would be at the top right, would swing back and forth to in response to, say, a seismic load. And so there is always some balancing out that you need to do to make sure that there's sufficient resistance. Now, with sophisticated computer models, we can usually handle all of these complex shapes without too much challenge in the X and Y or Z direction. In the old days, it was harder to do that. And so using simple calculation methods, usually based on hand calculations, everything was made simpler by having a symmetrical system and having a very clear lateral load resisting system. And so for low-rise office buildings, the classic system was a central core to provide the lateral resisting, and then the columns at the perimeter all took gravity loads, and then a diaphragm of the floor slab delivered wind and seismic loads to the red drawn core. We can get much more complicated, but recognize that that complication, while it takes a little bit extra effort to calculate, could take a lot extra effort to build, and that's where the money comes in. In low-rise buildings, 1, 2, 3 stories, lateral load resisting systems don't have to be as strong because they don't have to resist as tall a building. And so you can distribute your lateral resisting systems to a rather, a small system in all of the perimeters. So if this were a 1-story wood frame dentist's office, each of those red items there could be a plywood sheathed 2x6 wood frame wall, and you would have plenty of lateral load resisting. On the other hand, if this were a 5-story wood frame residential building, then it would be challenging because the loads would have grown enough that there may not be enough strength shown in the red lateral resisting systems, and they would need some additional lateral resisting systems like braces or something like that. Now, I'd mentioned it's quite important to keep things symmetrical if you can and want to do it simply, because if you don't, then the building will twist. And that's okay, provided you're calculating to accommodate the amount of deflection caused by the twist. And you have sufficient strength, of course. So the trick here is to minimize these eccentricities to lateral load by trying to make the centroid of the lateral load resisting system's resistance align with the centroid of, for example, either the seismic load action or the wind load action. It's very rare that you ever get them exactly aligned, but you try and minimize the eccentricity so that the floor doesn't twist or the building doesn't twist as it goes up. And so that's why we often see symmetry deployed extensively in buildings. It's economical, it's easier to build, more reliable to calculate without effort. And so this is why for many buildings we choose this approach first. We can build almost any shape if economics don't play a role. Now, I've been showing you red rectangles on plans of buildings so far in this lecture. Now I want you to dig into what are those red rectangles. Well, now I'm going to give you a vertical elevation. So looking at the side of that red rectangle, we have actually 3 systems with a small 4th one that I'll cover at the end. That's for special situations. The most common one that you would know would be the braced frame on the left, but there's also a rigid frame approach, and then there are shear walls, which is shown as the 3rd on the right. So Ching actually does a good job in chapter 2 of his textbook, talking about each of these types of systems and the importance of diaphragms, and we can put diagonal braces, which are usually the least expensive and the stiffest system, but they will obstruct, for example, windows and doors. And that's why moment frames have the flexibility that I can put an opening anywhere I like, including the full opening. And shear walls, as long as I don't put a hole too large inside that solid shear wall, I can get away with that. And we'll look at practical examples. Now, as I said, these rigid frame, shear walls, and brace frames all rely on having a diaphragm. The diaphragm needs to transmit those horizontal loads and spread them to these lateral resisting systems. Just keep that in mind. So let's start with shear walls, which is probably the oldest way of doing this, and that is make a solid wall. So in this case, the solid wall would be simply an opaque masonry wall, plywood sheathed wall, solid CLT, and historically brick and concrete masonry walls. Now, to make them strong and stiff enough, they have to be, have a width to height ratio. So here the width I'm showing is height over 2, height over 4, would be about as far as you'd want to go. Technically, it's possible to get more slender walls. It's just that they become more and more flexible. And so that's where you have to start calculating. But from an economics point of view, and if you want to put any holes in them, having that width W be somewhere in the half of the height is quite effective. And many practical shear walls are even wider than that. They will have a width that's equal to their height. And that means that they really act in shear. They don't act in bending. So what do these things look like? Well, in lower rise historic buildings, they look like the drawing on the left, or the image on the left, where that entire masonry wall is a shear wall, weakened by the holes, but there's so much wall that it kind of works out. The real challenge occurs as you are at the bottom of the building, at those storefront openings. Those are the largest openings, and that's also where the most lateral load will have accumulated. And so that's where the structural engineer has to sharpen their pencil, and she may need to add some additional bracing elements down on that first floor to make up for the large holes provided by the windows. On the right-hand side, we see a local, relatively recent concrete masonry unit building. And you can see that that concrete masonry unit, there's enough lengths of it that are pretty solid going in one direction at least to be quite a good shear wall resisting element. Now, we might choose to use a shear wall, solid wall in one direction and not a solid wall in the other direction. But these images I'm showing you here are for relatively tall concrete buildings, which are called pierced shear walls. A large proportion of the concrete does have holes in it. However, there's still enough concrete and none of the holes are so large that you don't get significant benefit of this rather significant area of the entire perimeter of the building. So on the right-hand side, we see that approach in the Waterloo barrel yard area. Concrete walls, holes punched in them, and provided that you get enough solid concrete, you can usually make this work if it's on the outside of the building and there's a lot of concrete. On the left side image here, we see that the end wall for this apartment building is a concrete shear wall, and you'll notice 0 holes. Very solid, very easy to imagine how you can build this 15 stories high. And what you can't see is that the shear wall in the other direction happens to be the corridor walls that separate the units. So down the middle of this building in the long axes is a shear wall formed by the concrete of the corridor walls. Similar approach being taken in this building where there is shear walls provided in the direction where you see those solid walls. This is a hotel/motel. And so having a solid concrete wall between apartment suites provides silence and fire protection. So CMU or concrete makes sense. And the walls to the corridor, which you can't quite see here, are providing the shear in the other direction. If you think of the walls that we can see, call that the X. Well, then in the Y direction, it's running down the corridors. And the only holes every room is a doorway and maybe a spot for some small ductwork. So this is kind of an approach that is used in a fair number of buildings. When you see those big, long, solid walls, you can be pretty sure that structural engineer was relying on them as a lateral load resisting system. Now, those lateral load systems called shear walls work really well for solid concrete, CMU, and wood sheathed buildings. But for steel buildings, you don't want to use a big chunk of steel, and it actually works out that diagonal bracing elements or braced frames work really well. These are probably the most material efficient solutions that we have. They're often very stiff. In cases we have to try and make them more flexible to manage seismic loads, so you can get them too stiff. But it's very common in steel, and I'm going to show you a whole bunch of photos of steel braced frames, which you have probably seen just driving around construction sites. On the left, we actually have a recreation center, the University of Waterloo Fieldhouse, and you see the bracing there is around the perimeter of the building. So usually you can see there's bracing in both directions, the X and the Y direction, if you look at the left and the right of the corner of that photograph. But the bracing doesn't have to be on the outside. Just like the shear wall, I can distribute my lateral load resisting system more towards the inside. And that's what we're seeing here on the right-hand side. We see that there is an X brace in the distant wall, the opaque distant wall, which happens to be the end wall of a retail establishment. But to keep the window openings very large and open for, it's a store to allow customers to look in and see what they should be buying, the braces are actually moved to the interior wall that you can see here. And so this is a very common integration of architectural needs, occupancy needs, where you put the X bracing. This would be a typical use of perimeter wall X bracing. The X brace that you're looking at is actually rather thin if you look at the scale of this building. This is about an 8.5 meter tall industrial warehouse. Those X braces are picking up a fair amount of load, and yet they're so efficient because they're in pure tension that they can be relatively small. In this case, I think they were 75 or 90 millimeter angles by 6 millimeters. And that X brace you see goes through the column at the middle, and that helps so that the part of the X brace that goes into compression when a load is applied doesn't buckle as much out of the way before those tension connectors kick right in. Now, this is a more recent, this is literally last winter construction project not far from the University of Waterloo. It's a grocery store. Floor to ceiling height here I think was 7.5 meters. And part of this was split into 2 stories. So the part on the right-hand side was the full store On the the left-hand side, you see a breakdown of what it looked like at a two-story section. And so we see an X-brace in both, and you can also get a closer look at the kind of connections. These braces seem to be taking a lot more load, and it is common today to make those heavier loaded braces out of hollow structural tube. Lighter weight braces often are made out of angle steel and occasionally out of rod, solid rod, but heavier loads tend to be into HSSs. They're very efficient systems for that, the steel efficient system. This is a 5-story office building in the Waterloo region, insurance company, and you can see the X-brace goes over 2 floors. But what I want you also to recognize is that the X-brace has been integrated with the location of where they're putting windows in this building. You can see there are no windows in the space between the 2 columns, so the architect doesn't have to work around the braces that are in there. Now, these X-braces are so obvious and clear signals that they're often integrated into the architecture. On the left-hand side, we have one of the first steel frame buildings that we know about. This is in France, as I believe it was 1797. It's the only photo I've ever been able to get of it. And you can see the X-bracing being used here so that they could have a tall and narrow warehouse actually at the docks, and only have relatively thin masonry walls. So this is the beginning of that engineering design approach. On the right-hand side, what we have is actually a building that is in an earthquake zone, California, near San Francisco. And what's interesting here is, again, they're proudly showing off the X-brace, and they're showing that you need more X-bracing as you get lower on the building because the lateral loads accumulate as you move down the structure. Now, what they're not showing you is that those X-braces will require painting and maintenance for the entire life, and will collect pigeon poo and seagulls and snow and icicles if they were in different climates than California. Now, we don't just have to use X-braces. Really, we're just using diagonal elements. So they're braced frames. This is the engineering lecture hall at the University of Waterloo. It's the addition on top of it. And the X-braces are put into the corner because that's where they didn't have any windows. But really, you can imagine that if you have an angle shown this way, which is actually with an HSS, and you do the other mirror image on the far corner, you end up with an X-brace. And this is a very strong, stiff, and efficient system. And you can get more creative than that. These are examples where the X-braces are built into the left-hand HSS frame, and that HSS frame is also acting as the columns, but it's looking like that because the architectural vision was to provide these sloped glazing units that you see on the right-hand side. So that's a diagonal drawing there. Here are some other braces. One of the features of both that last building and this building is that we have pre-made diagonal elements. These elements tend to come full length on the truck, welded up in the shop. That's why they're narrower. They fit in the 2.4 to 3 meter width that will fit on a truck, and they can be 12 meters, 14 meters long. So you can weld the whole thing up in the shop, lift this frame, if you will, bolt it down, and then attach the beams in between, and it makes assembly quite efficient. We do use X-bracing a lot on high-rise buildings, although less perhaps than we used to. This is an example of a steel-framed building, happens to be in Singapore. And we also build frames where the braces are sometimes made of concrete. So again, this is in Asia, where concrete has a cost advantage and labor wasn't as expensive. So you can put up with the cost of making formed reinforced concrete columns. But it's possible, it's just not common because of economics. There's no technical reason. This is an example of a building in Waterloo Research Park, and you can see the X braces of the core of the building shown there. I'm highlighting it with red. And as we walk into the building, you can see the X bracing for a larger, taller building. It was still only about 3 stories tall. You can see the size of the braces have grown. It's collecting more area. These are probably 25 centimeter square HSSs, relatively thin walls, but still, starting to get to be chunky. And the connections at the bottoms and the tops now need to be able to transfer that kind of load. Here we see an example where there is, in this building, also in Waterloo, I know structurally it's been designed to take advantage of not just the lateral resistance at the perimeter X braces, but also the core hidden in behind. And so the core is near the middle of the building, contains the emergency exit stairwells and elevators. That's enclosed in a concrete masonry exterior, which is both fire and sound resistance, and it could be deployed to resist lateral loads. But rather than enhance the strength of that core to take the loads of this whole building, they integrated these braced frames that they could pre-assemble. So this is a common economical solution. We even sometimes see X bracing used for low-rise buildings of relatively thin amounts of material. This is a 2-story building using flat straps of cold form steel, which can be quite stiff and strong. But the challenge is to make sure that you can transfer the loads. The end connections become the critical thing. This is something that is quite common in low-rise wood frame buildings, to use what's called a let-in brace. By let-in, they cut a slice in the studs, insert a T-shaped piece of metal, and then nail it. And it keeps the building square and does deal with some lateral resistance when you don't have OSB or plywood sheathing to provide that lateral resistance. Now, if the loads get higher, like I said, in multi-story buildings or significant seismic zones, or custom homes with large windows, like 5-meter wide windows, then we have to find other ways to get a structural bracing. And this is an example from Japan where, because of the seismic rules, they would quite commonly use wood diagonal bracing, even on a 2-story wood frame house, which is what this is. Now, the last of the common load resisting elements is called a rigid frame or a moment frame. This means that the vertical elements and the horizontal elements are connected to resist bending moments. They tend to be expensive because of the cost to do the connection. They tend to be expensive because of materials, but they give us those openings that can be important for particular architectural applications. We're even using these somewhat for garage door openings on single-family homes. So if you have a 6-meter wide garage door opening, 2.5 meters high, that's a large opening in a wall. And so there are increasing solutions that try and use moment frames if you have the money to pay for it. Now, I don't want to make it sound like moment frames are really expensive. They are expensive to pull off in some kinds of wood and some kinds of steel. But it's quite simple and inexpensive to get a moment frame in reinforced concrete design, because the rebar and the pouring of the concrete makes the joint connected, and it's pretty straightforward to put the steel in such a way to transfer moments. So buildings made of reinforced site cast concrete, routinely use rigid frames as a way of stopping the building from falling over. And so here we have E5. The elevator core probably provides some lateral resistance, but the moment resistance of the columns to slab will also provide a lot of lateral resistance. And in steel buildings that are tall enough, we routinely will see really heavy steel sections that can be used to frame an opening. And this is a rigid moment system. It's how First Canadian Place in Toronto was famously built. Had a lot of economic advantages because of construction speed and simplicity. For lower rise buildings, we sometimes see this in small sheds and pavilions because, again, the simplicity of the construction overcomes the additional cost of the materials. And this happens to be just a shed, a farm shed in Scotland with very simple galvanized connections that can be bolted together and very quickly produce a shed. Where we see a lot of moment frames is in pre-engineered buildings, pre-engineered steel buildings that I'll show you. And notice in this three-dimensional image here, we're dealing with this happens to be an arena in Canada, well, actually multiple arenas. It's 136 feet in one axis and 500 feet in the other, so it's a significant building. It's a couple acres under roof. But see the X-bracing to act as a roof diaphragm and the X-bracing in the walls to provide lateral resistance. This is what a pre-engineered steel moment frame looks like out of that building. They're able to shape the steel to match the worst load cases, and the lateral resistance here is not just provided by the beams, it's also by the X-bracing, but these have significant ability to resist lateral loads. So the X-braces can be far away at the ends of the walls, not right near the middle. And so you must have seen buildings like this in your life. Looking around buildings, you can see both of these happens to be rec center / arenas. So a common solution. And once we have this shaped frame of steel, then we put cross purlins on it and start producing the building enclosure, which we're going to get to in our next module. But sometimes we use these steel frames even on top of a concrete building, and we mix and match a moment frame of concrete on the bottom, but then a steel braced frame or moment frame on top. So the last load resisting element, I'll call it the fourth one, is not really used that often, but it has its place and you need to know about it. And so I call this the post, where we plant it in the ground or anchor it in a concrete foundation, and it is simply something like a flagpole resisting the load. And this can be really useful for particular architectural needs. One place we see it a lot are in pavilions, where the lateral resistance of this pole barn on the right-hand side is simply provided by the moment resistance of those columns embedded in the ground about 1.2 or 1.5 meters. But for most industrial commercial architecture, it's more likely that we'll see either posts. In this case, we could have a moment frame to make this canopy and walkway entry. But when we look at this example of a canopy, that, very likely is relying on moment resistance of the vertical posts to allow this slender beam in between. But it would be either a rigid frame or a cantilevered vertical post or some combo. And then at this point now, there's no way that we can say that this is being resisted by anything other than the vertical cantilever post. There's one post and all of the loads, both gravity and wind loads and lateral earthquake loads, all being taken by a moment connected post. And we usually see it for these types of architectural purposes where it allows a special type of building. So here I'm showing, and then the combination where we're starting to see some cable-supported canopies with a cantilever post that you can see has got to be pretty beefy, right? Architecturally, I think the shapes for some of these materials are less than appealing, but structurally they make sense at the very least. So that was a really fast romp through structural systems with a focus on lateral resisting systems. So you should be able to identify what is a shear wall, braced frame, rigid frame, understand a bit about the pros and cons and practical manifestations of what they are, and recognize that while some systems, lend themselves well to certain materials, don't get too narrow-minded. We absolutely do see flat sheets of steel used as shear walls in some buildings, and we absolutely do see braces made out of concrete, but those are rare. Just keep your mind open to the possibility that they exist, and understand that in any structure, a building structure, you're going to have to find out, how does the diaphragm work? What are the lateral load resisting systems? How does that side loads get down to the ground?